In the 70 years since the advent of the digital computer, these machines have become steadily more powerful and ubiquitous. Yet the biological brain is still unsurpassed in its ability to perform sophisticated tasks of sensory perception, planning, and execution in a compact volume and using very little power. Why can't we build computers that mimic the brain and are equally compact and efficient? In about 2004, computer scientists at the IBM Almaden Research Center began to ponder this question. In November 2008, this team was awarded a contract under the DARPA Synapse program, which enabled them to design and build new generations of neuromorphic chips that mimic the function of the biological brain's neurons and synapses. Systems built around these groundbreaking chips grew from 0 to 64 million neurons in 10 years, a scaling of 8x per year. This is the story of how that happened, the TrueNorth Journey. The IBM Almaden Research Center in San Jose, California, is the site of an annual event called the Almaden Institute that brings together leaders from industry, academia, and the government.
Almaden Institute is a very special kind of an event. Almaden Institute is a forum. It is a dialogue. It is an exchange. The goal is to learn from each other. But the ultimate goal of Almaden Institute is to stir up constructive action that leads to significant positive change in the direction of science, technology, business, and society at large.
In 2006, the topic was cognitive computing.
Cognitive computing is a study of computer science-style hardware and software, algorithms, and architectures that are consistent with known body of facts about neuroscience and exhibit cognitive phenomena. Cognitive computing is about engineering the mind by reverse engineering the brain.
2 years later, DARPA, the Defense Advanced Research Projects Agency, called for proposals for a new program called Synapse, Systems of Neuromorphic, Adaptive, Plastic, Scalable Electronics. The program's ambitious goal was to create groundbreaking new approaches to intelligent machine design that would be scalable to biological levels, yet would consume little power and occupy a small volume. On November 20th, IBM Research announced that it, along with partners from several prominent universities, had been selected as one of 3 teams to receive funding. And that's when things really started moving fast. The IBM team looked for clues to building a cognitive computer at the intersection of neuroscience, supercomputing, and nanotechnology, all fields that had seen an explosion of progress in the past few decades. Looking first to neuroscience, they studied decades of research on the connections in the brain of the macaque monkey, creating the most comprehensive map of its long-distance network. Armed with this information, the team modeled networks of neurons and synapses for simulation on conventional computers to explore what key features would need to be included in future neuromorphic chips. A series of these simulations on IBM Blue Gene supercomputers, increasing in scale from mouse and rat to cat to human, verified fundamental design principles and scalability. By 2010, enough was known to start building silicon chips. To test the basic concepts, 2 prototype chips were built. Both had 256 neurons, about the number found in the nervous system of a worm, but Golden Gate had a larger number of synapses, while San Francisco had the ability to change its synaptic values as it operated. Both worked exactly as designed. Even with only 256 neurons, these chips were capable of simple cognitive behavior. Playing Pong, recognizing handwritten digits, driving a simple simulated car. But the significance of these first chips lay not in what they could do, but in what they pointed to: true north. The first chips implemented only 256 neurons. How could the next chip be scaled to much larger numbers of neurons and synapses? The idea that emerged from the first chips and earlier simulations was that of a network of neurosynaptic cores, essentially a two-dimensional array of an improved, shrunk-down version of the Golden Gate chip. Each core would contain 256 neurons and 65,536 synapses, with all the information and instructions needed to perform its role stored locally within the core. The chip as a whole would have 1 million neurons and 256 million synapses. Cores would operate independently and in parallel, communicating with each other through an on-chip network, sending messages called spikes to indicate neuron activity. Work would be performed only when there was work to do, leading to low power consumption. While the hardware team worked on the design and fabrication of the chip, the software team created a simulator that exactly mimicked the chip's function. This simulator, known as Compass, enabled reliable development of applications before the chip itself became available. In June 2013, fabricated wafers arrived. With 5.4 billion transistors, the TrueNorth chip was, at the time, one of the largest in the world and the largest IBM had ever made. Packaged and tested, it was found to work perfectly, a testament to its modular design. And it consumed only about 100 milliwatts, 1,000 times less than a typical CPU, allowing it to run cool. The question now was, what can it do? The TrueNorth chip is an inference engine. A neural network must be trained offline using conventional computers, but once trained, the learned network parameters can be loaded into the TrueNorth chip, which can perform efficient, rapid, low-power inference. The TrueNorth chip, like the brain, processes spikes. Using TrueNorth requires translating the sensory input to be processed into the language of spikes, as well as interpreting the output in terms of spikes. The TrueNorth chip can be tiled with other TrueNorth chips to accommodate larger neural networks. Built-in circuitry permits the chip to send spikes to a location on another chip just as easily as to a location on the same chip. The TrueNorth chip is the basis for an extensive hardware-software ecosystem that includes tools for efficiently mapping neural networks onto TrueNorth systems. This ecosystem has enabled the development of numerous applications using this unique neuromorphic hardware. The chip's low power requirements make it ideal for mobile and robotic applications.
I see a car. I see a bird. I see a plane.
Traditional cameras create arrays of pixels, but a new generation of retinal cameras mimic the way the eye processes visual information, producing spikes in response to changes in intensity. These spikes can be fed directly into TrueNorth for processing, bypassing the image transduction step necessary when using traditional cameras. One application of this technology is gesture recognition, which can then be used to control a television set. Other applications include perception of optic flow, and stereo vision. Audio information can also be represented as spikes and processed by TrueNorth.
In wage negotiations, the industry bargains as a unit with a single union. Artificial intelligence is for real.
All the preceding applications were performed using a single TrueNorth chip and the NS1E evaluation board. If more boards are available, several networks can be run concurrently. Here, each of 12 boards runs a network train to play a classic Atari video game. The NS16E board takes advantage of the native tileability of the TrueNorth chip, creating a system that can run a model 16 times bigger than a single chip can accommodate. 4 such boards, packaged together in the NS16E4 system, can simultaneously run 4 such models, making possible real-time processing of large images. For the past 10 years, TrueNorth has been a direction guiding the development of new brain-inspired computers. This technology has spread to research labs around the world. Over 200 partners at more than 50 institutions have used TrueNorth in their own research after being trained to efficiently employ TrueNorth hardware and software. Over the 10-year life of this project, it has gained media attention from around the world. Won numerous awards, and been featured on the covers of journals and magazines. The success of this project is a direct result of the quality and commitment of the team involved. IBMers who leveraged the company's internal technical breadth and depth, and partners who provided a perspective from outside. They are the heroes of this story.